Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vectors and Geometry of Space. And this video is the second part of lecture number 3, dot product. And from the first video, we talk about the dot product definitions, what is a dot product, and then we also talk about, we derive a very important formula. We say, what is the angle between the two vectors, right? So how do we find that? Then the third thing we did is, for the dot product is how do we find the scalar projection of a vector to another vector, or we call, find the vector projections from one vector to the another. So those are the three things we did for the first video. So now for the second video, we're going to start to take a look at one of the application in physics. So we call this work, right? So how do we define the work and how do we use the dot product to do that? Okay, so let me go to our worksheets we did. Okay, so from the previous video, like I say, we stopped here, talk about the scalar projection and vector projections. And then now let's take a look at the work, okay? So I think if you are the physics major, this one should be very you sound very familiar, right? So in here, so let's see here. So the work is done by a constant force moving an object along a directed line segment by a vector A. So the work is F dot A. The vector A is what we call the displacement vectors here, all right? Okay, so A is the displacement vectors here. So let's take a look, right? So in here, number 8, we said find the amount of the work done by a horizontal force of 4 newtons here. This is a horizontal force of the 4 newton. And moving an object 3 meters up a hill and with a 30 degrees angle. And this 30 degrees angle is the horizontal ground here, all right? So that's why let's say, take a look, this is the graphs here. So I want to see what is the work has been done here, all right? So now let's first take a look at what is the displacement, right? So the displacement vectors here, right? So D is equal to, because I'm moving this object up the hill 3 meters with 30 degrees. So I always have an X direction and Y directions, right? For the vectors here. So for this displacement, I have the X coordinates and the Y coordinate. So what is the X coordinates here? X coordinates is here, right? So it's X coordinates, Y coordinates. So the cosine 30 is equal to the X coordinates with the hypotenuse. So the same way, so that's why the X coordinates will be the 3 times what? Cosine 30. So the same way for the Y coordinates will be the 3 times what? The sine 30, correct? Okay, so if you put into a calculator or you use your unit circle, so the X coordinates will be square root of the 3 over square root of the 3 times 3 over 2 and the 3/2. So this is what is my displacement when I move along. So that's why it's my X go here, Y go there. That's what is in here, right? So that's what is this graph. This thing is showing you. And then I have a horizontal force, right? So because this is a horizontal force, so what is my F here? The horizontal, that means I only have X components. I don't have the Y. So this is 4 what? 4 zeros here, right? So the work has been done is the force, right? So it's the force times dot product, the displacement. So this will be the 40 dot product square root of the 3 over square root of the 3 times 3 over 2 and the 3/2 here, all right? And now in here, what do we have here? So if you do that, and then we have here, this is the 6 square roots of the 3, and we know the units here is joules, right? Okay. All right. So that's what is this problem. So this is kind of like the application problem for the physics major, and if you know how to, if you know how to use it, the definition, then you just need to be careful. Right now you are in a like the in the XY directions here. Okay, so now the next ones here, let's take a look. The next ones here, let me see here. The next ones, next slide here. Okay, so the next slide, my mouse got stuck. Okay, now, okay, it's working. Okay, this is the another definitions, and this definition we call is the directional angles. So the directional angles, basically, like if you have vectors, right? So that if you have vectors in the spaces here, I want to find angles of this vector to the x-axis, y-axis, and z-axis here. Okay, so here we need to be careful. Yes, this is angle is in the positive x-axis, positive y-axis, positive z-axis here. All right, so that means the angle should be between the interval of 0 and the pi, 0 and the pi here. Okay, so here, the graph here, let me try to see, maybe can help you to understand how that works here, right? So this is a 3-dimension. Probably it is not that easy. Let me try to draw it. Okay, so hopefully you can see. Okay. So here. Okay, so take a look, right? It's like a box, right? So this is your vectors here, right? Take a look. So it seems like it's in the box, right? So now, probably, if you look at the Z, it will be easier, right? So this is the alpha, beta, gamma. So this is the gamma angle to the, for this vector to the z's here, right? Okay, so now if you take a look at this one, probably it's easier to see because x and y is kind of a little difficult. So that means you are projecting this triangle. So this is the right angles here, right? So this is the triangles here. So that's why the gamma, so it will be what? It will be, so it's adjacent over hypotenuse, right? So what is the adjacency here? So the adjacent is the A3, is the A3 components. And then what is hypotenuse here? The hypotenuse is the length of what? The length of the vector A here, right? Okay, so then you can use the semi, so that's why in here, right? So you can use so that's what in here, right? So it's A3 over the length, right? So because of in here, so this is what? This is the adjacent side of this gamma angle. So this adjacent side, that's the components of the vectors, the A3s, right? So that's what is the A3 over A. So the same thing you can see from the alpha to the x-axis, beta to the y-axis. This is what we call this directional cosine or the directional angle, alpha, beta, and the gamma here, okay? And so they said that, the reason why this is we like it, so because it is defined which directions and this vector goes here. All right, so now let's take a look at some problems here. Let's do some first couple problems are very mechanical. So let's see, make sure we know how to do it, right? So they say find the directional cosine of A. So the first one, I need to find the length of the A. So what is the length of the A here? Is 9 plus 1 plus 16. So what I have is the square roots of the 26, right? So for this one, I can write it as 3, -1, the 4 here. So the cosine, so let's hear the cosine. They want to see the directional. So I said the cosine alpha is just the A1 components is 3 over square roots of 26. Then cosine beta will just be -1 over cosine 26. Then cosine gamma is equal to the 4 over square roots of the 26. Correct? All right, that is what we call is a directional cosine. And then now I want to find the angle. So they just take arc cosines, right? So I said alpha is just equal to the arc cosine 3 over square roots of the 26. And the beta is just equal to the arc cosine, what? -1 square roots of the 26. And the gamma is just equal to the arc cosine 4 over square roots of the 26. Then use your calculator, you will get this about 54 degrees. And this is about 101 degrees. And this is about 38 degrees, right? So now you can kind of picture that, what is where is the vector goes here. Okay, so now let's take a look. Let's say what may be conclude about vectors. All right, so whose directional cosine is a cosine alpha equal to 0, cosine beta equal to -1, and the cosine gamma equal to 0. So I know, when the cosine alpha equal to 0, that means alpha has to be what? Alpha has to be like in the 90 degrees, right? So then we know the only non-zero vector V will be what? The V is a point pointing at the direction of negative y-axis. It's kind of like makes sense, right? So like in here, so if this is your coordinates here, right? So this is x, y, z. So let's see here, if you have vectors here, let's say our answer say, hey, it has to be this vector, right? So as you see here, this vector, so this angles here has to be what? 90 degrees angles, right? Because x, y. So, right, this one is kind of hard to say, so, oh, it's 90 degree, but if you have x, y here, right? So it's 90 degrees here, right? So the same ways here, the y to here to the z axis, right? So the z-axis here, this one's here is 90 degrees also. That's why you guess both got 0. Then the betas here is -1. Why? Because from here, right? So from here to here, what is the angle? 180 degrees. So I know the cosine 180 is -1 here. All right, so the problem number 10. So this is a very good kind of concept problem. So make sure you understand what is the directional cosine means. Okay, last ones here. They say what may be conclude if a force F try to move an object along the directions A orthogonal to F here. All right, so that means if this is your F here and your displacement is going like here, like this is the A vectors here, right? So I know the work, right? So it's the F dot A. Because they are orthogonal, what is that? So that means is what? Is 0, right? So what it means is 0, that means no work is done, correct? If no work is done, what's that mean? That means the object is what? Does not move. Clear? Right? so the last two problems are the kind of application problems about what we learned. So this is the second video. It's a pretty short video, but we talk about a couple, like the application. So one is how do you define the work? It's a force dot product displacement vector. And then what is a directional angle? That means if you have a vector in the R3, you'll be able to see what is this vector point to, right? Because then it's the angle between the x-axis, y-axis, and the z-axis. That's it. That is our lecture number 3. It's a little bit longer lecture than the other, so that's why we break it into 2 videos here. All right, so it's nice to talk to you. And then our next lectures, like the lecture 4, we're going to talk about another vector operation. That's what we call it, a cross product. So what is the meaning of that and how do we do that? All right, that's it. And so it's nice to talk to you and I hope you get a good understanding about the dot product. Not only mechanical part, how do you do it, and then also the application part. All right, so that's it. You have a good day and looking forward to talk to you in our next lectures here, lecture number 4. Okay, bye.